The second video lab report consisted of filming an object falling vertically and somewhat slowly to later analyze the motion. I decided to film an empty carton soap box of mass 3.2 grams falling from an initial velocity of 0 meters per second. As I have probably mentioned in last lab report, Newton's second law states that the acceleration in a system depends on the system's mass and the sum of the forces acting on the system. This video lab report was also based on an adapted version of Newton's second law that may predict a system's velocity. Two motion predictions were made to later be compared to the actual experiment. The first prediction involved one and only one external force acting on the object, gravity, while the second prediction involved two different external forces acting on the object, gravity and drag force. Let's start by looking at the analysis done on Tracker. I would like to point out the fact that the soap box looks blurry at some point of the video. I had to calculate the point of mass at every frame where the object was blurry. The data used this time to establish the calibration stick was my height, 1.74 meters. Here's the calibration stick. Now talking about the axis, the origin was placed at the first point of mass of the object. The horizontal axis is the x-axis and the vertical axis is the y-axis. The whole coordinate axis system was tilted a little bit for the camera was not completely straight. As it can be seen from the graph I will show later, the change in position started to be greater as time passed. This will be explained in further detail as this video goes on. There are two different predictions based on computational models for this second video lab report. As in the first lab, the fundamental principle on which the predictions are based is the adapted version of Newton's second law. Let's go to Python, to the actual code. Some important physical data we must include in the code of the computational model are the following. The mass of the box soap is 0.0032 kilograms. The initial velocity of the object is equal to 0 because it starts from rest. The time when we choose to start analyzing is 0. The initial position of the ball based on the assigned axis is 0 as well. Last frame finishing at time t equals 0.693 seconds. Here it is. And finally constants g, which is equal to 9.8 meters per second squared, and b, which was approximated to be equal to 0.00266. This was based on the actual final position of the object. This time for the computational models, there are some forces acting on the system. The net force is not equal to 0. For the first computational model prediction, only gravity is taken into consideration for the sum of the forces acting on the object falling. Here is the graph yielded from such model. For the second computational model, drag force is also taken into consideration for the net force acting on the system. Here is the graph comparing both predictions and the actual experimentation. It can be seen that the change in position is greater as time passes by. That's why the graph is curved. As you can see, the final bounces the box made after hitting the floor or surface affected the data extracted from Tracker. These movements can be seen here. If analyzing velocity versus time as time passes, velocity increases due to the net force acting on the system. This can also be seen when examining the increasing change in position as time passes. In the model that did not take drag force into consideration, the velocity has a greater increase as time passes. In the model that did include the drag force, the velocity has a smaller increase, and this happens because the drag force has a direction opposite to velocity. The model with drag force is more realistic for this, and is a model that may predict a terminal velocity. Here it is. The yellow arrow points at the gravity force acting, and the blue arrow points at the drag force. If the object was initially thrown downward instead of starting from rest, the terminal velocity would have been greater than this experiment that again began from rest. Based on the adapted version of Newton's second law for prediction of an object's motion, initial velocity is added to the net forces divided by the mass and multiplied by delta t in order to get the final velocity. If the initial velocity is 0, the whole final velocity will be less than in another case where the initial velocity is actually greater than 0. In conclusion, as Newton's second law states, external forces affect an object's final velocity after any change in time. Overall, the computational models that predict the object's motion are similar to the actual observations and data that yielded from the experiment. The fact that the last movements made by the box generated from an impact between the object and the surface helps me and the audience realize that an object falling should only be analyzed until the box hits the surface. No further data should be taken into account for the experiment. Thank you.